Good morning from this part of the world. Is about 4 minutes after 10 a.m. West African time. I would like to thank and welcome all of you to this second series of our webinar. It was a great time during the first webinar session, and we look forward to having a more fruitful time together today. Let me welcome those of you that are just joining us on this second series. I believe that you all got an email with a link to our previous webinar where some of the items that were treated during that time can be consulted. So feel relaxed. I don't think that you have missed anything so much. You can always go back to those materials to consult for proper understanding. At this point, I would like to yield the floor to our trainers. Thank you all, and I hope at the end of today, we will all be happy for putting our time to go through this together. Thank you very much.
Thank you very much, Dr. Omodara. So yes, from our side also, welcome to everybody to the webinar. And I give the floor now to Dr. Torres.
Thank you very much, Anna, and thank you very much, Dr. Omodara. It's a pleasure being here today again in our second webinar session after the one we had in March. Let me go through our schedule today so that we can have a look what we had done in our last session and what we will be doing today. First of all, for the ones that are attending today for the first time, I would like to introduce our brand SelfChill, which is a brand for modular cooling solutions powered by solar. This is a technology engineer in Germany by the company Solar Cooling Engineering and distributed in Germany by the solar company Faesan. And in Nigeria, we have a long-term cooperation, as you know, with NISPRI, the Nigerian Store Products Research Institute in Ilorin, which is hosting this series of webinars and will be hosting also a face-to-face training in September this year. In the country, our technologies are locally produced and distributed by the company EcoTutu. And as you remember from our last webinar, we had a look to the cooling requirements of agricultural foods. We had a look to the different configurations that we can have for solar cooling systems. We had a very deep overview of the working principle of refrigeration machines. So I recommend, if you haven't seen it yet, the link of the first webinar, because you were not there and you didn't see the video yet, I will encourage you to have a look to that so that you can have this basic knowledge. And we had, after a lunch break, an overview of the different components and some examples of the cold room. Today, we are focusing a lot on the equations, on the design methods, and we are not going to have a lunch break as we did last time, but we will, of course, have a small break in between the session to have a small break. After my introduction today, we will bring you, all of you, as a panelist, because in this session we would like to have more contact with you so that you can make questions, turn on your video, say something, and we can respond to your questions on the during the presentation, so to say, because we are going to do a lot of calculations. As you were informed already, we will calculate the cooling curves of the product. We will calculate the cooling demand. So we will deal with thermal losses, the energy we need to cool down a product, so to say. Also, we'll have a look to the design of ice storage systems, which is very crucial for our technology. And of course, I will provide you with a basic knowledge for the design of PV and batteries. On July 5th, the third webinar will take place with an overview of the design method. So the same equations we are doing today, but with a computational model. So we will be working with Excel files so that you will be able to design your own cold room with our support. So for that webinar, we will provide you also an Excel file before. Okay, so today we are talking about equations, all equations you need to design a cold room. So before I continue, I would like to remind you the values we have with our partnership with the brand SelfSeal and with the institutions that are representing this technology in Nigeria. So as you know, we are solar power. We support the use of solar energy, of course, but not only that, we also support the use of low global warming potential refrigerants. As you can see here, this is very important for sustainability because as I mentioned last time, the use of conventional refrigerants is having a negatively impact to climate. We also promote the use of ice storage, thermal storage, for example, as you are seeing here, so that we can reduce the amount of electrical batteries that we need. And as I told you already, we promote the local production. Our products are made in Africa, in the case of Nigeria, by the company Ekotutu. Okay, so let's go deep into the topic of today, just to bring you to the basics of solar cooling. As you know, the refrigeration machines we can use are several. We talked last time about evaporative cooling. There are also solar cooling that is done with solar thermal modules, absorption cooling. We might have also with photovoltaics panels, thermoelectric Peltier cooling. You can find it in a small refrigerator. So we are focusing in vapor compression heat pumps, which are run by PV panels. Yeah, so this is all you need to know today. And the basics on the vapor compression heat pumps we had already. We will still talk about the most important equations today. So with our solar cooling unit that is connected to solar panels or solar panels with batteries, we can create different modular cooling solutions, and we are focusing today in our cold room. So the cold room with thermal storage, you can see here. So I'm trying to bring you again back to the components, because I thought before we go deep into the equations, it will be good to remind the components we are using. So we are focusing on this system, even though with the same technology, we can realize also milk cooling systems or ice blocks makers. Okay, so let's go deeper in detail of the different components. So you can see here the PV panels, of course, which are needed to run the solar power cold room. What else do we have? We have, of course, a cold cell where we are storing our products, so the insulated room. We are having cooling units, as you can see here, charge controllers. So the PV panels are connected to the charge controllers that are here, that are charging the batteries here on the bottom. And then we have our cooling units. You can see them here. They are immersed in water in our water chiller. So this is the blue box here. And you can see a picture of this over here. So you see here the cooling units, 3 on each side, depending on the cold room size and so on. That's why we are doing the design process today together. And you see here the cooling units are immersed in water so that ice can be produced. And we have always a cold water available that is then pumped to a heat exchanger, as you can see here. I will show you the components live in a minute, but just I would like first to have the understanding here on the slides. Why is important to have thermal storage? With thermal storage, we can reduce a lot the use of electrical or the need of electrical batteries. So we can during the day store the solar energy in ice and then use the cold water at night to cool down our products. If we will do it like this, then our compressor can only work a couple of hours per day, as you can see here. So when the solar radiation is available, so to say, but we will have here some losses, yeah, some solar energy that we cannot use. That's why we support the use of small batteries so that we can use this energy at night for a couple of hours. So we get additional cooling energy that is somehow coming from the surplus energy. And then we can also, after sunset, produce a bit more of ice, always having small batteries. That's why, even though we have thermal storage, we also use electrical batteries, small electrical batteries. And at the end of this session, you will have a look why we are doing this, and you will be able, as a designer, to go for bigger batteries or smaller batteries, more or less cooling units. This will be, at the end of the day, your decision, and this is a decision that is based on the cost of the cooling units, the cost of the batteries, and so on. But today we will come to a design of a cold room so that we can go through this process together. What else? We have PV panels, we have batteries, but we discussed in the last session that we have a primary and a secondary system. So you see here PV panels for the primary system. What is the primary system? The primary system is providing energy to the cooling units. So this primary system, always when we are talking about the primary system, is the PV panels, batteries, cooling units that we need to create the cold energy that we need to cool down our products in the cold room. And then we have also a secondary system. Yeah, why do we need a secondary system? The secondary system is there to run the water pump, as you can see here, the water pump and the heat exchanger. So this secondary system is there to provide us energy so that we have electricity at night or during rainy days to pump the cold water from the water chiller to the heat exchanger so that at the end of the day we produce cold air. The secondary system is designed in a way that we have always enough electricity, even though imagine we are at night, the cooling units are not working, but we have the secondary system that is having enough electricity to run the water pump and the fan of the heat exchanger. That's why we divide it into separated systems, because the primary system can run actually without batteries, yeah? It is your decision if you have more or less batteries, but the secondary system always needs batteries for the small energy consumption of the water pump and of the fan, the heat exchanger fan. Okay, so here you see a picture of a water chiller in Nigeria at NISPRI in Ilorin. So you see here there are different methods of constructing the water chiller. You see here the cooling units inside of the cold room. And now I had the idea, why not showing you the components here at our facilities in Memmingen in Germany, so that you see also a little bit where we are and how we are continuously further developing our technology. What I would like to show you is our cold room here. So you see the water chiller and the cold room. First of all, let's go to the roots. Let's go to see the PV panels that are here outside. We have 6 cooling units and 1 PV panel for each cooling unit that you can see here. So 6 cooling units, and here you see 1, 2, 3 PV panels of 350 watt peak each, and here another 3. So 1 PV panel per cooling unit. And then we have for the secondary system, we have here other PV panels that have in total 600 watt peak. Okay, let's go inside. By the way, I will show you also the facilities of Faesan here on the back. So the distributor of all self-chill components with their offices upstairs and the warehouse downstairs. Just that you have seen it today. We have today a very sunny day, so quite cold. And this is the solar cooling engineering research hall. So let's go inside and have a look how we are connecting the cooling units to the system. So we have just seen the PV panels, right? So the PV panels are connected here to the charge controllers. So you see here the connection for PV and then the connection for the batteries. These are maximum power point charge controllers that make the system run at maximum power. Then you see here the batteries we are using. And then the charge controllers are connected here to the battery protect systems that are allowing the cooling units to consume energy only when the voltage is high enough. Yeah. And you can see here the cooling units, how they are installed. Okay, we have 3 cooling units on each side. And let's now open the water chiller. So the cooling units are only working when solar energy is there and the batteries are charged. And this is your decision if you use batteries or not and how deep you discharge the batteries. It's a design question, yeah, that we will deal today. And then you see here the evaporator plates of the cooling units that are immersed in water. And at the moment, we have turned the water pump and the heat exchanger on so that you can see how the cooling energy is transported inside the cold room. So you see the outlet of the water chiller down there. It's going through the water pump. Let's follow that here from the back. So you see we have the outlet of the water chiller. Then we have a water filter and our water pump that is here. This water pump is connected to the secondary system. And then we have the insulated pipes here going all the way around inside the cold room. So let's go inside the cold room. And you see the cold water coming through the fan coil inside the heat exchanger. It's just some water pipes with heat exchanger, which is this component. And then we have our fan here that is taking warm air from the cold room and delivering cold air here to the cold room. Okay. Then the water is coming back to the water chiller. It's coming back to the water chiller here to the top. So that will be this pipe. And the water is here coming back, as you can see. So it's a closed system. During the day, we are producing cold water, at some stage ice. And during the night, the cooling units are stopped and the cold water here with the ice are providing cooling energy to the cold room. This is a slide I had also in the last session of the webinar, which is describing quite well the different considerations that need to take place for the design process of a cold room. So it is important to know the specifications of the products we are using. So first of all, we need to understand the commodities that we are storing in our cold room, as you can see here. Then we need to consider also how the cold cell is going to look like. Here you see also Yeah, with refrigerants are you using, which cooling system, and so on, with thermal storage, without. We had that already last time in our webinar. For the time being, we are today focusing on our self-chill cold rooms with thermal storage. You see here also monitoring issues and so on. But what is today our focus is here the cooling demand. So how much energy do I need to produce to deliver enough cooling energy to my system? So you see here several steps, the heat load, power demand, and so on, electrical supply, is this going to be run by solar, how exactly, and so on. And are we using thermal storage? Yes, no, and how to plan it. So we are today dealing with this topic. So we will have this under control so that when somebody needs to have a cold room that needs to store a certain amount of a certain product, we can actually say, okay, the cold room should be like this. It should be run by this amount of PV panels, this amount of cooling units. This is how the system would look like. I have the design and I have a cost for this, because you will discover today the different conditions or specifications modify a lot or affect a lot to the cost of the system. So you will see today, for example, it makes a difference having the cold room in one or other city in Nigeria because of the different weather conditions. It makes a difference on that. It makes also a difference if you are storing products at 5 degrees or at 10 degrees. This makes a huge difference in the design, and the most important, the amount of products that you need to cool down every day. This is the most important factor at the end of the day. To get a feeling on that, we are going to go through an example together. I thought it will be a good idea to have to design a cold room that is operating in Nigeria, in your capital, Abuja or Lagos, yeah, just to compare both locations. I have some diagrams today to do that. Why not storing tomatoes? Yeah, I have written down here in the season between March and September. For a solar cooling system, we would like to utilize the cold room all over the year. Yeah, but we are going to concentrate in this season. And tomatoes, need a temperature of around 10 degrees or no less than 10 degrees. So we will design the system for 10 degrees, and the cold room size will be 20 cubic meters, as you can see here. So this is the sample we are going to have today, and we will be having a look to the different equations based on what we have here. First of all, and if you remember, it is important that you always consider the product optimal conditions, so the specifications for the product. A tomato is, for example, one product that can be affected by chilling injury. It means when you are cooling down too much or too fast, or perhaps cooling down when the tomatoes are not yet ripe enough, then you are going to cause some injuries in the product. So first of all, we'll be at this stage to inform ourselves about the best practices for storing tomatoes in our case, and to find an optimum between having slowing the ripening process and avoiding chilling injuries. Therefore, we recommended in the last webinar session to use an app, or you can also have access via website to this link. This is a data bank of different commodities, fruits and vegetables, and the specifications for optimal store conditions. So if you remember from the last webinar, we have the optimal temperature, we have the optimal relative humidity, then we have the topic of sensibility to ethylene gas, if it's emitting ethylene gas and if it's sensitive to ethylene gas. And then we talk also about the topic of what's happened with CO2 when the product is having respiration, consuming oxygen and emitting CO2, what's happened to the product quality? Yeah, do we need to have ventilation? Yes or no? So those are the most important factors. And if you will go to the website directly, I just copy a couple of facts that I found related to tomatoes. And I found very interesting the recommendations that are done there to have the best quality and the longer shelf time by harvesting the tomatoes green and storing them at the beginning at a higher temperature. So you see here 12 to 15 degrees is the best for the first phase of ripening, and at some time the best storage temperature is something between 10 and 12 degrees. Yeah. When the tomato is ripe, then the temperature could be even lower, as you can see here, but that's why I consider to use 10 degrees for our case, but I found very interesting the whole recommendations that are provided here. So this is the first thing we need to understand together with the final user, yeah, of the cold room, so that we can get the best out of the cold room, right? Our focus is to make the system generate the maximum income that can generate. For example, if you will have a look together with the user to the prices of tomatoes, for example, in May, then you will see the latest you sell tomatoes in May, the most, the higher the price is. So this will be one of the possible income generation potential of the cold room. So this is something related to the business model, but is affecting also the design of the cold room. So we need to understand this very well. And regarding the relative humidity, it is important to control the humidity for a relative humidity between 90 and 95%. Below 90%, we will have the product drying, so that it doesn't look anymore at it's supposed to look like. Yeah, you can see it here to prevent water loss. Okay. At some time, I also saw that it is important not to have high CO2 concentrations inside the cold room. This you can see yourself under responsive to control atmosphere, so that you have the whole picture of the product we are using or any other product you are interested in. First, the first question we are asking ourselves is how fast is a tomato? In this case, you can see in the slide an apple. Any product, how fast is this cooling down, right? One recommendation for tomato is to have a fast cooling after harvest. Fast cooling down to at least 13 degrees. So this was a recommendation. So we are interested to cool down our products fast, but the product has some thermal properties, and depending on this, they will cool down faster or slower. And I would like to go through the equations with you. This is something we are not going to calculate today in detail, but we will have that calculated through the Excel tool in our next webinar. So you see here one example for an apple, yeah, that has a similar size than a tomato. So if we are applying 5 degrees cold air to an apple that was originally at 30 degrees, then this is the cooling curve we are expecting. Yeah, so we have the center in red and the surface in green. So you see in the first hour here, nothing is happening. Yeah, because the cooling energy or hasn't, the apple in the middle is not feeling the coldness yet. And the surface is decreasing the temperature, as you can see, and it takes actually more than 5 hours to cool down an apple from 30 degrees to 5 degrees. So you can see it here. Okay, so it is not like this that we are putting a product in the cold room and then it is cold. Yeah. Imagine when you have also several grades at the same time, then you have to make sure the ventilation, the circulation of water is given so that the products can cool down fast. So this is something important if you are putting, for example, a lot of tomato crates inside the cold room at the beginning without taking care of ventilation, air circulation, then probably it will take more than 24 hours to achieve the temperature you want to achieve. That's why we need always to think about this, perhaps having a pre-cooling space where we can put the crates, have a pre-cooling on them with direct air circulation, and then put them somehow once they are cooled down in some corners of the cold room for long-term storage. Okay, which equations can we use to calculate the cooling process of a product? Let's have a look here. Imagine a product is simplified by a geometrical shape, like a sphere in this case. Then we can use an equation like this. We start here with this equation. So we have the temperature of the product depends on the temperature of the air, of course, on the air around it. It depends also on the initial temperature, as you can see here, initial temperature, and then it depends, we have here the LOR number, and then we have here the time, T small, and then we have here tau. Tau is the time constant. So the bigger the tau is, the slower the product will cool down. Yeah, and this tau is depending on geometrical and physical parameters. You can see it here, tau. It depends on the density. You see here, rho density. It depends on the heat capacity, C. Yeah, and it depends on the volume, on the numerator. Yeah, so if density is high, if heat capacity is high, if the volume is high, then tau, the time constant, will be high. This means the cooling curve will be slow, right? Big products with big heat capacity, with big density, they take longer to cool down than products with low density, low heat capacity, or low volume. This is, I think, clear for all of us. And then we have here H. H is the heat transfer coefficient between the surface of the product and the air surrounding the product. Okay, so, and then we have also surface, the surface of the product. So if surface is big, if the heat transfer coefficient between the surface and the air is big, then the tau, the time constant, will be low. This means the cooling curve is fast. Yeah, the product is cooling down fast. So the calculation of all these parameters in this equation is giving us a feeling how fast the product will cool down. Yeah, so if you have a watermelon that is this big, you can calculate here and you will see the cooling curve is quite slow. For this case, you might need to have a pre-cooling chamber, or perhaps you want to use cold water to cool down the product quicker. Yeah, so we need to understand this so that we can recommend our final users to use a pre-cooling method or another one. I'm not going to go into detail on this today, but we are having a look to the equation so that you have in your hand how to estimate this cooling curve. But all products are, of course, not an sphere. That's why to calculate the volume and to calculate the surface is not an easy task, but no problem. They are scientifics that has been having a look to this, researchers having a look to this, and have came to the conclusion that almost all agricultural produce can be simplified with this geometrical shape, prolate spheroid. Yeah, this is a shape that has one axis C, and the other two axes are the same size, A and A. Yeah. Compared to an sphere, yeah, to calculate the volume and the surface of an sphere, it is easy, yeah, with these equations. For a prolate spheroid, it's a little bit more complicated. We can have a look to the equations here. For the surface, it is like this, the equations you need to use. And for the volume, you have the equation here. Okay. It looks complicated, but at the end of the day, we just program these equations in Excel and then we can use them. And these equations are programmed in the Excel design toolbox that we will provide you for the next webinar. Okay, then we have our cooling curve, but you might be wondering, okay, where do I get the other parameters from, right? I have here the heat transfer coefficient, yeah, convection coefficient to the cooling medium, surface to air, surface and volume. We had already the equations, but what about the heat capacity? How do I calculate it? Or the heat conduction of the inside the product? How can I calculate this? For this, we need to use some literature. We need to go into the internet or have a look to several books. I have written here a couple of, I have used a couple of tables that are providing us this data. Yeah, for example, for the heat transfer between the air and the product. Yeah, here this is also depending on the air velocity. Yeah, so if you are now having ventilation inside the cold room and you are having apples like here, then you will have a heat transfer coefficient of 11 watts per square meter and degree. If you are having a ventilator, as is our case, then you will have in more and more air speed. Yes, I could tell you in our cold rooms, we are having around 1 square meter per second in average in the cold room, so we can be dealing with these heat transfer coefficients. Yeah, 26 more or less. This depends also on the product. So you will see here different products. So we'll have to have a look, for example, for tomatoes. What is the heat transfer coefficient? What else? The heat capacity is, of course, very important. There are two ways of calculating this. The first one is also going into a book, or in this case, there are also online some sites that are providing this information as this link of Engineering Toolbox. There you will find for the different products the heat capacity in different units and so on. What I like even more, because the heat capacity is dominated by the amount of water that a product has. And what I like more is this equation here that you can use for all products, all agricultural produce. This equation is telling you the heat capacity depending on the mass fraction of water. So the mass fraction of solids in food. So if you know the initial humidity, moisture content of your produce, then you can calculate the heat capacity. And this is what we are using also in our Excel toolboxes. So you can use one or the other, the equation, the simplification, or you just get the value from from the literature or from the web. Don't forget to divide. So if you are getting the heat capacity in these units, kilojoule per kg and Kelvin, you can divide it by 3.6, and then you get it in watt-hour per kg and Kelvin, which is more convenient for our equations. You will see later on, we are always talking about watt-hours, kilowatts hours, or watts, and so on. So if you have it already on the right unit, that will be easier for you. What else? We have the heat conduction. So how is the coldness or the thermal energy transferring the product itself? And here we have also several tables. I have here one table, or also here a link where you can have a look to this. So you see here in apples, and then you have here the thermal conductivity in watts per meter and Kelvin. Okay, then we have everything we need. We can program the equation. We have calculated our tau, our time constant, and then we can get the cooling curve in a very easy way. What's happening if we want to know also the temperature in the center of the product and the surface of the product? Then we use the same equation, but with an additional factor. You can see it here, the factor J. And this factor J is something experimental that is described in the refrigeration handbook of the International Refrigeration Association. I have extracted the diagrams for you here. For this, you need to calculate the Biot number that is depending on the conductivity and the size of the product. So you have here the equation. And then once you have the Biot number, you go here to the table, and depending on the shape of your product, then you get this factor J that you introduce in the equation, and then you have from the average cooling curve, you get it for the surface and for the center. Yeah. This is all programmed in the SL toolbox you will get for the next webinar, right? So today we are providing you with all the equations so that you know how this computational model is working, and also to give you the chance to program these equations also yourself. So we have the average cooling curve, and then with this J parameter, you get it for the center or for the surface. That's all what you can do with these diagrams. Okay, congratulations, you have survived the first difficult equations. Now the next ones will be always easier. So we have calculated how fast a product will cool down inside our storage room. Please don't hesitate to make any question, put it on the chat, or in the best case in our Q&A chat. So you can find both in the Zoom software, and please let us know if you have a question. I will be very happy to answer it in the middle of the presentation. Of course, you don't have to wait until the end. Okay, so now we know how fast a product is cooling down. What else do we need to know? We need to know, okay, this product is cooling this fast, but how much energy do I need to cool it down, right? The one question is how fast is cooling down. The other question is how much energy do I need, and how much power is this power having taking place at the beginning or at the end? What's going on there? As you could imagine, if you are cooling down a product that is cooling down very fast, then you need a lot of cooling power, right? Because this product is able to absorb a lot of energy. So you need to deliver a lot of energy, right? To cooling down at this speed. If we have big products that are cooling down very slowly, then the energy, the power you need will be lower. Yeah. The overall energy will be always the same. It will be I mean, if you are having 1 ton of tomatoes and 1 ton of watermelons, the cooling energy you need to cool down the products will be the same, yeah, similar, not the same, similar. But if you are having tomatoes, the tomatoes are cooling down faster, so you can provide more cooling power, right? So they require more cooling power to cool down at this speed. I hope this is understandable. This is something we'll have a look also with the design toolbox, because based on the cooling curve, we will calculate the cooling power we need for cooling down those products.
Victor, there is one question.
Perfect.
Can we have different fruit products in the cold room? For example, mango, watermelon, and banana.
Yeah, this is a very, very important question. This is something we deal with on the last webinar, where we said we need to take care, because we need to make sure the products are compatible with each other, and they have to be compatible in 3 different aspects, or almost 4. The first one is the temperature. Are the products feeling well in the same temperature? We saw in the last webinar that some products are not compatible with each other. For example, avocados and bananas. We saw we cannot store them together. Yeah, avocados have to be at 7.5 degrees, and they don't allow a huge range. And bananas cannot be below 13 degrees, so they cannot be together, for example. Then relative humidity. If you are having onions, you cannot store them with carrots. Carrots like to have the ambient very humid. Onions, they need to have very dry air. They won't be compatible there. And then we have also the ethylene problematic. So we cannot store, for example, mangoes with cucumbers, yeah, because mangoes emit ethylene, cucumbers are sensitive to ethylene. The same will happen with CO2 in the cold room. Some products might be sensitive to CO2 that are emitted by other products. So we need to consider this, but no problem, because as you saw before, we have the information from the university in California. They have a wonderful data bank of this. So you just have a look to the different produce you wanted to store, put together. You have to figure out if they are compatible with each other. By the way, the University of California has also developed product groups. So I think they have around 4 product groups, so that they tell you already this group is compatible with each other, this other group is compatible with each other, and this other group is compatible with each other. That might help you also for this. Once you realize, hey, I have 2 products that I want to store at the same season, at the same time, and they are not compatible with each other, then you have technical options. You can, for example, have a cold room with 2 separated cold room chambers, with 2 separated cold chambers, so to say. They will be provided with cooling energy at different temperatures, for example, and they are not sharing the same atmosphere. So this is one option, and this is normally what is done at cooperative level, at farmer level, because yeah, this is happening, that they are not compatible. I hope this is responding the question. So a very important topic. We need to inform ourselves very well about the optimal conditions of the products and the compatibility. But the good news is we can also create several cooling chambers, and this is not having a big impact in the cost. It's just you have a separated door, the same cold room with 2 doors with 2 different chambers. That's all. Coming back to our slide here, the heat transfer during cooling process. So we talked already about the heat extracted from the product, so the energy we need to cool down the product. Then we have the fact that the product itself is producing energy, yeah, as you know. because a product, a agricultural product, a commodity is a living plant. They are having respiration, so they are consuming oxygen and emitting CO2, and consuming energy, as we do also. We need to consider this, because if you have a huge amount of produce in the storage room, this might be a number of kilowatts or watts that are generated in heat, because the products are there, not because we are cooling them down. It's just because they are there. They are stored in the cold room. Very nice. We'll have a look to the equations later. And then we have the thermal losses. Thermal losses, because we have outside 30 degrees and inside we want to have 10 degrees. We have a 13 insulation, so we are having losses of cooling energy, or we are having thermal energy, hot energy coming inside the cold room. You know, talking about cooling energy is not scientifically correct. It's just about thermal energy. We are extracting energy of the cold room, but I like talking about cooling energy because it is easier to understand. Okay, what else do we have when we open the door, right? What's happening? Warm air is entering the cold rooms, or we might have air infiltrations. This warm air going inside the cold room is consuming energy to get cooled down again. And what is here very interesting is not only cooling down the air. If we are in a humid environment, like in Lagos, for example, where you have humidities around 80% all over the year, then you are not only getting warm air, you are also getting humid air inside the cold room. That's why you need to cool down the air, and you will have condensation of water that you need to extract also, and that is consuming energy. We'll have a look to this in a minute, in a couple of slides. And then we have the equipments and internal loads inside the cold room. We might have a ventilator inside. We might have persons going inside, staying inside for a while, things like this that we need to consider. Okay, as a summary of this, the cooling load is a sum of different factors. So we have the Q product, the energy to cool down the product, the respiration energy that is generated by the product. Then we have the energy to cool down the air. Then we have the energy that we need to keep the cold room cold, thermal losses. And then we have the heat generated by ventilators, pumps, persons inside the cold room. So we have 5 factors to consider to calculate the cooling load of an storage room. Now we are going to have a look to them one by one and calculate them and see the equations we are using. The first one, the sensible heat of the product. We want to cool down the product. As we said before, we want to know how much energy we need to cool down 500 kg tomatoes from 20 degrees to 10 degrees, for example. That will be a case that we will have in our sample. So we are having tomatoes. They are outside at 20 degrees, and we want to put them inside the cold room to cool them down from 20 to 10 degrees. So we have here the Q product. The mass, we said 500 kg. Then we have the heat capacity. We could take this from a table or calculate it from the equation. As discussed previously, we can take 0.95 watt-hour per kg. And then we have our delta T, that is 20 minus 10 is 10 degrees. Okay, somebody here will be willing to do the equation and put it in the chat. Actually, it's a very simple calculation, right? Because this is almost 1 times 500 times 10, sorry. So we have 5,000 watts hour, which are more or less 5 kilowatts hour. Yeah, a little bit less on this. Okay, 5 kilowatts hour per day. If we are entering the tomatoes every day or once a week, depending on this, we will calculate it the cooling load. So a very important equation, very important equation. You know it, you know this well from your studies. Mass times heat capacity times delta T. This is telling us the energy. How fast this energy is going to be consumed depends on the cooling curve, right? So if the cooling curve is fast, this energy will be consumed very fast. If the cooling curve is slow, then this energy will be consumed along a longer period of time. Okay, so we have already our first calculation, the energy extracted to cool down 500 kg tomatoes in the cold room. Thank you very much, Charles. 4.7 kilowatt hour is what we need. We will write it down. 4.75 kilowatt hour is the energy we need to cool down 500 kg tomatoes from 20 degrees to 10 degrees. If this is happening every day, then this is the cooling load every day. Okay, respiration. Let's have a look to this. We need to go to the literature, to go to the internet. At the University of California, in their tool, they provide this also. They call it rate of respiration. And you have to find out what is the watts per kg or the milliwatts per kg. This depends also on the temperature. We are working at 10 degrees. I think we don't have tomatoes here in this table, but I found it out for you. This is around 60 milliwatts per kg at 10 degrees. So more or less this 60 milliwatts per kg. And have a look to this. If you are having, for example, asparagus, they have they generate a lot of energy. Yeah, so for some products this is more important than for others. Yeah, so we'll have here, you see tomatoes. If you have a look here to the other products, tomatoes is not generating a lot of heat. Yeah, but anyways, we like to calculate it. So if we have 500 kg, so the Q of respiration will be our mass multiplied by this rate of respiration. So we said 60 milliwatt per kg. So who is able to calculate this? Please indicate also the units. So we have here 500 kgs. So it's easy to calculate in this case, yeah, 3000, okay, 3000 watt, 3000 milliwatts, 3000 milliwatts. So 3 watts. So this is, as you can see, not so much. But what's happened if you have a store in the cold room actually 5 tons, yeah? Then you will have here a higher number.
Victor?
Yes?
Is it times 30? It should be 30,000 times 60.
Exactly. I did a mistake. Yeah, I was wondering the whole time.
From your equation here, you say Q has
Mm. . Yeah, exactly. Thank you very much. This is 30 watts. You see, even with simple calculations, I was doing here a mistake. So we have 30 watts. 30 watts. How much is this all over one day? How much energy do we need here? Because this is the power, the energy is always power times the time, right? So we multiply here times 24 hours. So the energy for respiration is how much? Very nice. Okay. We are having here help 0.7 kilowatts hour per day, right? Per day. Okay, so it is not so less, right? So we have 0.7 kilowatt hour per day. And this is only for half a ton, only for 500 kg. So if we will have 5 tons already inside, yeah, then we'll have to multiply this by 10, right? So then we'll have 7 kilowatt hour per day, which is a lot, right? So please consider this. It is not too much, but also not something you can like not consider, right? It's something important. Okay, let's go ahead. We have already 2 factors. We have here the heat extracted from the product, the respiration. What is coming next? The hot, humid air inside the cool room. And this is a little bit more challenging to calculate because we need to have knowledge on the psychrometrics diagram. I hope most of you have knowledge on the psychrometric chart, on the psychrometric diagram. For those of you that haven't seen this before or doesn't have knowledge on the psychrometric diagram, don't worry because you will understand it in the next minute. The psychrometric chart is telling us the properties of air. And you know, air is not just a gas, it's also water vapor as a mixture. And that's why we cannot use the equation we used before to say, okay, I have mass, I have heat capacity, and I have delta T. It is not working like this for air. Or let's put it like this, it's only working like this if you are not having saturation of water in the air. Let's have an example. You see here in the psychrometric diagram many things, but don't worry. Let's have a look here to the first one. You see here temperature, air temperature, 50 degrees, 40 degrees, 30 degrees. Yeah, this is the temperature of the air. So let's focus. We have 35 degrees, for example. So we will be moving in this line. We are moving in this line. Relative humidity, you see here, starting from 100%, 90, 80%, 60%, 50, 40%, and so on. Relative humidity. So if you know the temperature of the air and the relative humidity of the air, you know already where you are in the psychrometric diagram. So if we consider we have 55% relative humidity, then we are here, okay? That's all. Very nice. You are already using the psychrometric chart. Now, what can we find out? We can find out what is the water content of the air. So we go here up, and you see here we have 21 grams per kg dry air, water content. Very nice. Very nice. What else can we know? We know the enthalpy of the air, the enthalpy of the air. In this case, 90 compared to air at 0 degrees, 90 kilojoules per kg dry air. You have it here. Very nice. So we have 4 parameters at the psychrometric diagram. We have dry temperature, we have water content, we have relative humidity, and we have the enthalpy, specific enthalpy of air. Very nice. If we are cooling down the air to, let's say, 30 degrees, yeah, then we will stay at this point, right? Everybody is following? We will be at this point. Here we are having sensible heat. Yeah, we are going from 35 degrees to 30 degrees. So delta T5. So we will have how much energy? We can calculate it with a psychrometric diagram. We are going from 90 to 85 kilojoules enthalpy. So we'll have here in this case 5 kilojoules per kg air that we need to cool down the air to this new temperature. This is matching to the equation we saw before. This equation, if you remember, this one. Oh, hold on. Sorry, I jumped too much. This equation is for sensible heat, mass Cp delta T. Yeah, with this we could calculate this cooling down the air from 35 degrees to 30 degrees. But what is the limitation of this equation? If we are cooling down the air to lower temperatures, which is the case in our cold room, as soon as we are coming to the saturation, this is this point, right? This air, by cooling down at, let's put it like this, follow this line, at 26 degrees, you see it here, 26 degrees, it is saturated. What does it mean? Now, from now on, you are not only cooling down the air, you are also condensing water. And condensing water requires a lot of energy. Yeah. And that's why we need to use the psychrometric chart to assess the amount of energy that we need to invest when we have hot air going inside our cold room. So let's have a look to this. What's happened? Imagine we are going now to 15 degrees. So we are cooling down and condensing water, sorry. And then we are coming here to this the cold room operation conditions. So we are now at 15 degrees. We're at 15 degrees. What else? What is the relative humidity? We'll have here 80% more or less. Yeah. What is the moisture content? We can see it here upside around 7. So we went from a water content of 21 grams per kg air to 7 grams kg air. So you see we have lost a lot of water. So you can even calculate how much condensed water you are generating. But it's not so important for us how much water we are condensing. What we want to know is how much energy we needed to invest, right? And for this, we need to consider the specific enthalpy of this point. So in this case is 35. So 35 minus the 90 we had. It's 55. So 75, 55, right? Kilojoules, thank you, by kg air. So this is the energy we need. And remember, if you want to have it in watt hour, then we divide it by 3.6. Okay, so now we have more or less, we have understood how to calculate this. Now we need to know how much kgs air we are going to cool down, yeah, and then we need to know how much volume is going to go inside the cold room. And as a recommendation, we can consider 2 renovations per day. 2 renovations renovations per day. If we have 20 cubic meters, then 2 times 20 cubic meters, 40 cubic meters of air that we are cooling down within the cold room. And this way we can calculate the amount of energy that we need.
Victor, sorry, what do you mean by renovation?
The renovation is when you open the door, then you are getting cold air going out and warm air going in, right? So the cold air is going from the bottom and the warm air is going from the top. And a recommendation for the design of cold rooms for a typical operation of a cold room is to consider that the air inside your cold room is renovated 2 times per day, so twice a day by the door openings. Yeah, so if you have a cold room that is always closed, then you don't need to consider this. Probably you are not having renovations, you are not having humid air going inside. But as soon you open the door, then you will have air going inside. This is something you just need to consider as an experience done by others that recommend to use this or this value, because it is difficult to calculate how much air is going inside when you are entering the room, right? That's why I think we discussed about that last week. It's so important to have PVC curtains in the door of the cold room, right? So that when you open the door, you minimize the amount of energy that is coming inside the cold room. So is that clear for?
Yes, thank you.
So we are not going to do this calculation now in detail. I think everybody can follow. I can tell you this will be, let me see if I can calculate it here quickly.
There is already an answer in the chat. Victor, you are muted.
Yeah, the calculation is good. Thank you, Oscar. But I came to 0.3 kilowatt hour per day because we have 2 renovations of 20 cubic meters each. Yeah. So you see, it is something also important to consider, but it is not like huge. Yeah. 0.3 kilowatt hour per day. What we need to cool down. Let's have it here to cool down the 2 renovations. So we are talking about 2 times 40 cubic meters. Then we need to multiply by the density of the air, which is 1.2. Yeah, and then we get to more or less 0.3 kilowatt hour per day. Yeah. Okay, so you see, compared to respiration, it's around half of it. Yeah. Okay, fantastic. Let's go ahead to the next. Well, actually, I had it calculated here in watt hour already. Okay, that's matching more or less. It's actually 0.4 kilowatt hour per day because of the density of air 1.2. Okay, fantastic. 0.4. Very nice. So we have already many things, yeah. We calculated here 4.7, here we have 0.7, now here we have 0.4. Okay, we are coming there, right? We have a good feeling. We are not forgetting anything. We are now going to a very crucial factor, which are the thermal losses, right? because we have inside 10 degrees and outside we have the ambient temperature, then we are having losses. Let's have a look how important this is, because this is going to tell us how important it is to have a good insulation or not, right? So let's go for that. First of all, we need to select the insulation material. Here, it is not important. Somebody willing to say something? Grace, Abel, you have unmuted yourself. No
I
question.
have nothing to say for now. No.
Oh, okay.
Thank you very much.
Yeah, no problem. For the insulation material, we need to know which material are we taking. Are we taking sandwich panels, polyurethane, yeah, which will have a insulation degree of 0.03 watts per meter and Kelvin thermal conductivity, or are we having something else? Yeah, are we having polystyrene here, which has a less thermal conductivity? We want to have, of course, a good insulation degree, right? But in this case, we need to have a look to the cost. So if we have a material that has less thermal conductivity but is cheaper, then we just have a higher thickness, right? So we need to figure out on the cost. So we cannot say the best material is the best insulator, yeah, because you can still work with more or less thickness. Imagine if we are having a natural insulator like wood or elephant grass, straw, whatever. Yeah, this is very sustainable. For example, the thermal conductivity is not so good. It means it is not a good insulator, but then we have a higher thickness, right? If this is sustainable and it is a cost efficiency, then we can have different materials used here. So at the moment we have been using sandwich panels a lot, polyurethane, but we are about to have also a cold room made of agricultural waste like straw, elephant grass, wood, and so on, because this is better for sustainability. Okay, but now what we want to have a look is to the equation, yeah? And this equation you know very well. When you want to calculate the thermal losses between a surface, then you need to know the surface, of course. You need to know the delta T, temperature outside minus the temperature inside. Then you need to know the lambda, which is the thermal conductivity that you have here in this table, right? Then you need to know the thickness you want to have. So for example, 800 millimeters or 100 millimeters, with our typical thickness of sandwich panels. And then you have here the time, yeah, because you get it, this is like the power, and then multiplied by the time you get the energy, yeah. Okay, let's have a look to this. How can we calculate this? We said we have a cold room of 20 cubic meters, yeah. Who could provide an estimation of the overall surface that we have? So we have here our cold room. It has 20 cubic meters. So now we are challenging your mathematical knowledge. We have a cold room that has 6 faces, right? And in total, we have 20 cubic meters. So our question is how much surface we have in total. So if we are here willing to calculate this A, the surface, the area, what is the total surface that we have? First of all, we need to figure out, okay, what are the dimensions of our cold room, right? So I can make you a suggestion. We have here 3 meters. 3 meters. We have here also 3 meters. And we have here 2.2 or 2.25 meters. And then if you multiply these 3 values, then you will come to 80 cubic meters, okay? But we still don't have the surface. Anybody willing to calculate this for us? So we have three different surfaces here, number 1, number 2, and number 3. Number 1 has a surface of 3 times 2.25. Number 2 has a surface of 3 times 2.25, so the same. And this surface has a surface, this surface, the area is 3 times 3, yeah. So at the end of the day, this is not such a difficult calculation. Area is equal to, we said we have 4 surfaces that are the same, right? So 4 times 3 times 2.25 plus the other surfaces here on the top and on the bottom, which are 2 surfaces with 3 times 3. So anyone willing to calculate this, please? It should be around 60 square meters. Okay. And now I will recommend also to use sandwich panels. Let's take this value for thermal conductivity. And then the thickness, I will recommend to have, let's say 80 millimeters. 80 millimeters. Okay, so somebody willing here to do also the equation as soon as we have the surface. Okay, thank you very much, Charles. 63 square meter surface. Very nice. 63 square meters. Wonderful. So now we have this value, delta T. We don't have now. Let's suppose we have 30 degrees outside and 10 degrees inside, which is going to be a worst case scenario, right? Actually, we should take an average temperature. Average temperature in Lagos, for example, will be 25 degrees. So if we take this better, so the delta T will be 25 degrees minus 10, so it's 15 degrees. And then we have here 0.035, and then the thickness 80 should be in meters, so 0.08. Okay, who is able to do this equation? I will do it also in parallel. 63 times 15 degrees times 0.035 divided by 0.08. Here you go. 413 watts. Okay, this is watts. And then if we multiply it by 24, do it in a second. Let's write it here. 413 watts times 24 hours per day is equal to 9.9 kilowatts hour. So almost 10 kilowatts hour. 9.9 kilowatts hour
Hello, Victor.
per day. Yes. Yes, kindly go ahead.
I'm presenting. What do you mean by the lambda and what do you mean by the head?
Yeah, the lambda is here the thermal conductivity. Here, what you have here on top. Thermal conductivity. And because we are taking sandwich panels with polyurethane, we are taking this
Okay.
0.035. And the L is the thickness of our sandwich panels. And now we are going to do in parallel what's happened if we have a thickness of 100 millimeters. Yeah, if we have a thickness of 100 millimeters, I will do the
Please go ahead. Go ahead, Victor. Go ahead.
Thank you. So if we have a thickness of 100 millimeters, so we'll have 7.9 kilowatt hour per day. Let's summarize it in the next slide. Oh, I had it here, the equations. Okay, let's summarize it here. So we said thermal losses, if we consider 25 degrees outside and 10 degrees inside, yeah, 20 cubic meters, and we said the thermal losses are 9.9 kilowatts hour, everything per day, okay? Per day for 80 millimeters insulation, the thickness, insulation thickness, and 7.9 kilowatts hour a day for 100 millimeters. Very nice, yeah? So you see, we can save 2 kilowatts hour per day if we use a better, higher thickness. The question I have to you, is this something we want to do, yes or no?
Sorry, Victor, there is one correction, maybe, of from Sonia in
Yes.
terms of the L.
Yeah, this is right. Yeah, it's 80 millimeters. They are divided by 1,000 is 0.08. It's right. It's also the way how I consider it in the equation. Sorry if I said it wrong. So in the equation we had here before, in the thickness 80 millimeters, what you take here on the L is in meters, is then 0.08 meters. Yeah. Okay. Thank you, Sonia. Good. Then the question is, yeah, which insulation are we taking? This is part of our design, right? And this we cannot know at this point of the design process because we don't know yet how much this is affecting to our PV, to our batteries, to our cooling units, right? This is what we will do in the next webinar, and this is going to do a lot of fun because then we will consider prices. And based on the design, we will be able to select, do we want to invest our money in insulation or do we want to invest our money in cooling units, PV panels? Yeah, it will be our decision. And this will depend on the cost. How much do we pay for a higher thickness of our insulated room, right? Is this something we find in Nigeria? Can we have 100 millimeters panels or perhaps 120 millimeter panels? How much do we pay? And based on this, we will get a feeling if this is important for us or not. From the engineering point of view, of course, we will say always, yes, the better we insulate, the better efficiency we get, right? But this is not all about efficiency. It is also about cost efficiency, right? And this is part of the design process. But now you have a feeling how to calculate both. So we have here the two variations, 9.9 kilowatt hour a day for 80 millimeters or 7.9 for 100 millimeters. Then if you remember, we had here also 4.7 for the product. We had here 0.7 and we had the air infiltration 0.4. Yeah. Okay, so what is the total cooling load? The total cooling load, we can write it like this. So it's the sum of all of them. Yeah, let's have a look to this. Let's work with the worst case, 80 millimeters insulation. Let me calculate it together with you. So I have here 15.7, 15.7, 15.7 kilowatt hour per day. Very nice. This is a very important number. This is very important that we need to know before we continue with the calculation of the thermal storage, the calculation of the PV panels, batteries, and so on. So congratulations, you are able to calculate the thermal load of a cold room. Of course, there's days that is hotter. There are days that are more sunny, less sunny. This is something we will do later with simulations and so on. But at least with these equations, we can calculate the worst case. And I encourage you to use always the equations at the beginning, because you can, as you have seen, you have your small equations and you already get a feeling. You don't need to trust a simulation model or some complicated equations or advices from others. With these equations, you have everything in your hand. Very nice. We forgot something, by the way, the equipment and the internal loads. This is not going to be big. What do we have inside our cold room is a ventilator, as you know, in the heat exchanger that consumes around 75 watts electricity. And this electricity is converted into heat, yeah, because it is inside the cold room. So if you multiply this by 24 hours, you will see this is not like a huge value, but anyway, something to consider. So 0.6 kilowatts hour, 0.6 kilowatts hour per day for the ventilator. And then we have persons inside the cold room. We don't have actually, yeah, one person going inside, putting the products there. Yeah, it's going to be a couple of minutes. But if you want to consider it, a person, depending on its condition, it produces 150 to 350 watts. So if you are 1 hour inside the cold room, then it will be 150 watts hour, right? More or less. So just for you to get a feeling. And now let's have a look to the calculations. I did it for 1 day. These Excel files you will get for the next webinar, but just for you to see how it is when you don't take average temperature, you take the real cooling process, the real ambient temperature. So you see here the cooling of the product all over 24 hours. So when we enter the product, we have more, and then it's always less. You see it here in this line, yeah, this blue line on the Q product. It's going down, as we said. Then the most important one here, the thermal losses in yellow, thermal losses, we have it here. So you see, depending on the ambient temperature, when it's hot, you have more thermal losses. During the night, it's colder, you have less thermal losses. That's why here these fluctuations. And then you have the infiltration and the respiration. I have it more or less constant, even though it is not constant, right? Air infiltration happens when you open the door, but we are not calculating this in this detail at this point. What else? Then we have the total cooling load curve. You see here in blue, and the total of it, in my calculation, Excel calculation, I came to 13.45. So it's less than what we calculated. No worries, we will keep on using our values, okay? But this is just for you to see, okay, what's happened when I calculate it with a Excel file. I can then do it hour by hour. I can actually calculate the whole year and so on. And this is how the curves look like in reality. Okay, and
Victor, sorry to
yes.
interrupt you. Maybe we can make a like 15 minutes break before we continue.
That's a very good idea. Thank you, Anna. What is coming next is actually the calculation of the cooling energy, electricity, and so on. So it's like the other part of the design of the of a solar power cold room. We have 15 to 1 o'clock here in Germany. It's supposed to be 15 to 12 in Nigeria, right? Now I will suggest a break of 15 minutes, if it's okay for everyone. Then this means we will be
It's okay. Thank you so much.
meeting at 12 o'clock Nigerian time. Please be punctual because we have 1 hour left for the webinar, and we still have 35 slides with very interesting content. So if you are on time, we will continue through the process of the design of a solar cold room. Thank you very much for your attention so far.
Thank you very much. You can also stay logged in, and then we will just on our cameras later on. Victor, you are muted.
Thank you, Anna. Hello, everyone. I hope you had a nice break. Thank you, Anna, also for the introduction of the tool for the optimal storage conditions for tomato. And now it's time to continue. As a reminder of what we did so far is we calculate the cooling load of a cold room, cooling down 500 kg tomatoes per day, 20 cubic meters, storage room at 10 degrees. And we came to around 15 kilowatts hour per day. But I saw the calculations I'm doing in the next slides are based to the calculation I did here. So I would ask you to consider or imagine we are using the 100 millimeter cold room so that we can come back to this value, yeah, around 13.5 kilowatt hour per day, because this is going to use in the next slides. Good, this is the total thermal energy, right? This is the thermal energy we need to deliver to the cold room to keep it cold and to cool down the products. But if you remember from our last webinar, we cannot say that this 13.5 kilowatts hour is also the electricity we need, right? Happily for us, because we are using vapor compression heat pumps, and they work with a coefficient of performance. This means they deliver more cooling energy than what they consume on electricity, right? If you remember from our last webinar. And this is calculated or somehow describe it with the coefficient of performance, COP. So the efficiency of refrigeration systems is measured by the coefficient of performance, COP, which indicates a ratio between the extracted heat or the cooling power divided by the electrical power or the energy consumption. So we have here on top our Q, which we calculated already, yeah, 13.5 kilowatt hour per day. And to be able to know how much power we need, how much electricity we need to invest, then we need to know the COP. Are there any ideas how to calculate the COP based on what you know from the last webinar? Because we need it now to calculate our electricity consumption. We need
Sorry, I think it is 15.7, not 13.5.
Exactly. We calculated 15.7, but because of my calculation on the next slides, I'm using 13.5. I kindly request for all of us to consider the cold cell with 100 millimeters. If you remember, it had 2 kilowatt hour per day less thermal load, so that we come to the 13.5 kilowatt hour. I need to do it like this because all my calculation after in the next slides are based on this value. Okay, so from now on, we consider thermal load, cooling load 13.5 kilowatt hour. And the question was, because we want to calculate the electrical energy we need to know the COP, the coefficient of performance. Are there any idea how to do this based on the knowledge you have from our last webinar session?
Probably, Victor, you could add this 13.5 for 10 millimeter thickness, or just
Exactly. Yeah. So this is what we are having for 100 millimeters insulation thickness. Yeah. Okay, now everybody's with me. Please write in the chat if you are following, if you have any idea on how we can go ahead with the COP. We will continue with the equations of the COP. COP is the cooling energy divided by the electrical power, right? Okay, and if you remember from the last webinar, we said we can calculate the ideal COP, the Carnot COP, if you remember. And this is depending on the warm temperature and the cold temperature. So the ambient temperature and the temperature inside the cold room, or in our case, the temperature in the water chiller, which is the place where we are creating the energy. So you have the possibility to calculate it with this equation, and then we said to get the real COP, we multiply by a ideality factor, which is around 25%. And then we get our COP real, yeah, depending on the temperatures. We are not going to go into this calculation now, but you are welcome to double check the numbers I'm going to show you in the next slides, not in the next slides, actually here. I calculated for you, if we have a cold temperature of minus 3.5, which is the temperature we normally have in the water chiller when we are producing ice. And depending on the ambient temperature, we will have these COPs. And now I would like to concentrate here in 30 degrees and operate with a COP of 1.75. This means if we consume 1 watt of electricity, the cooling unit deliver 1.75 watts thermal energy, cold energy in this case. This means if our cold room has a thermal energy consumption of 13.5 kilowatt hour per day, and we consider an average COP of 1.75, which is a worst case, Then we'll have a maximum electricity consumption of 7.7 kilowatt hour per day, 7.68 kilowatt hour per day electrical energy. And this is what normally solar experts need to calculate the solar system, right? In our case, it is even more complex because we have the thermal storage, but at least we have already a number we can base to keep on calculating the solar systems. So everybody following so far, this is the electrical energy consumption that we can expect for our cold room, and this energy needs to be delivered from the PV panels. Okay, very nice. Then we'll have a look to the solar components we need. I think that not all of you are experts on solar energy. That's why I decided to have a couple of slides to introduce the solar components. That's for you to have seen them once. So we have the PV panels, of course, that you can see here. Then they are connected to a charge controller with MPP tracker or without. This is not so important now. MPP tracker get the highest efficiency from the PV panels, but this is also a question of the price. And then we have batteries connected to the charge controller. Sometimes we have in solar system inverters, but as you know, they are not needed for us because our cooling units work on DC current, direct drive, direct current. This means we don't need inverter. We might need batteries if we want to use them, as I saw before, and then out of the cooling units are connected here and are producing ice, which is then needed for the cold room. Okay, let's have a look to the PV panels. There are different PV panels types, as you know, monocrystalline, polycrystalline, and others. In the meantime, the monocrystalline solar panels are very well established because they are the ones with the highest efficiency, and they are not expensive as they used to be. So they are actually in the same level than polycrystalline panels. They have this efficiency more or less, but this is not now important for us, the efficiency of the PV panel, because as you know, the PV panel itself has a watt peak power indication, and I would like to explain it to you for the ones that haven't heard about it. So every PV panel has a 13 indication of the watt peak or kilowatt peak. This is the maximum power of a PV panel, and the explanation why it is done like this, it is because a solar panel, it is converting the solar radiation into electricity, right? But we have solar fluctuations. So sometimes it is more sunny, then we have a cloud, then sometimes it's hotter, it's colder. So it is difficult to say, okay, this PV panel has this surface and this efficiency, because this is not helping us so much because we don't know what are going to be the conditions. And that's why we use the watt peak indication that is telling us, so the watt peak rating is showing us the power that can be generated by a solar panel at its peak rating. And the peak rating is 1000 watt-hour per square meter and ambient temperature 25 degrees. So if we have this solar radiation, this is normally happening in the middle of the day, and we have this ambient temperature. Actually, this is also the cell temperature. Then we will have the watt peak indicated in the panel. For example, the PV panels I showed you before, they have 350 watt peak per PV panel. And then we know, okay, under these conditions, they will generate 350 watts. And then we know. but I guess you still don't know so well how to deal with this. And I will tell you in a minute. What is very important for the watt peak is that you can multiply it by the solar global horizontal irradiance. This is the amount of solar energy that has arrived to the ground all over one day. And this solar radiation, we'll put it here. Some persons, they mention it like a G. Others, they say this is the solar horizontal irradiation, yeah, or irradiance. This is defined in kilowatts hour per square meter and per day. And this you can find under any weather database, so to say. You can know how much kilowatt hour per square meter per day do I have in Lagos as an average, right? We will have a look to this in a second, but I can tell you already, in a very sunny day, the solar horizontal irradiance is about 6 kilowatt hour per square meter. In a very rainy day, let's say in Lagos, rainy season, totally cloudy, you will never be below 2 kilowatt hour per square meter and day. So the solar irradiance is plus 218. And to know the amount of electricity that our PV panel can generate, we just need to multiply. So to know let's use better energy. So the energy generated by a PV panel is equal the solar or horizontal irradiance times the watt peaks. Yeah. So if we have here, for example, 6 kilowatt hour per square meter multiplied by 350 watt peak, how much is this in energy? 350 times 6. So we have 2.1. So 6 times 3.50 is 2.1 kilowatts. Sorry, kilowatts hour per day. So a PV panel with 350 watt peak rate at a very sunny day in Lagos will deliver us with 2.1 kilowatt hour per day. And that's why it is so nice to work with the watt peak, because then you just multiply by the solar irradiance and get the amount of energy you are getting during this day. So this is quite important for PV panels. It is not important how efficient your PV panel is. What is important is how much you pay per watt peak, right? If the efficiency is low, you will have a higher surface. If the efficiency is high, you will have a lower surface. But what is important for you is how much you pay per watt peak. It also doesn't matter if you are using 2 or 3 smaller panels or one big one. At the end of the day, what counts is the cost efficiency per watt peak. So the specific cost per watt peak of your PV panels. I hope this is helping for the ones that are not familiar with PV panels. Let's continue. What is the next components? We have here the batteries. There are different type of batteries. You can divide them by the chemistry that they use. We have lead acid batteries. We have lithium ion batteries. You have heard about both. And with lead acid, we have wet batteries that are not anymore used. These are the batteries that used to be used for vehicles, where you needed to put also some distilled water inside. We have AGM batteries and gel batteries. I don't want to go into detail. Gel batteries and AGM batteries are very commonly used for solar systems. We use them. Gel batteries have a higher overall life, than AGM, and AGM are the cheapest one, so to say. Lithium batteries have a better energy density, have a much longer lifetime, but are, as you know, also more expensive. So this is also a part of the design process that we will have. Today, we are not deciding which battery we exactly take. Today, we are deciding how big the battery should be in terms of energy. And the same for the PV panels. We will calculate how many watt peaks do we need to run our cold room. But this is just a first introduction. How to measure the battery capacity, most of you know, but for those that are not familiar with this, the battery capacity is defined on amperes hours. Yeah, so if we have a battery having 100 amperes hours, it means it will deliver us 1 ampere 100 hours or 100 amperes 1 hour, right? So this is how the batteries are defined on the capacity, but the energy capacity normally we want to have in watt hours. So we multiply the amperes hours times the battery voltage. This means if we have a battery of 100 amperes hour and it has 12 volts, then by multiplying this, then we have 1.2 kilowatt hour battery, right? So you can say both. My battery has 100 amperes at 12 volts, or my battery has 1.2 kilowatt hour. And then in this case, you are not saying the voltage because this is an energy indication. Then we have the battery's state of charge, SOC. As you can see here, this is telling us how charged the battery is: 100%, fully charged, 0%, totally discharged. And I can tell you lead acid batteries, they cannot be discharged. They shouldn't be discharged below 50%. Because then the lifetime of the battery won't be high. To know the state of charge of a battery, you can measure the voltage. Yeah, if you measure the voltage of a 12-volt battery and discover it has 12.43, then you can know, okay, it has a state of charge of 80%. Okay, just for you to get a feeling on this, for the ones that are not familiar with this. If we are discharging the batteries always to 0%, then the lifetime will be very short. You see here the dip of discharge, which is what is the minimum COC that you have always, right? So if you are discharging to 50%, from 100% to 50%, then you have a DOD of 50%. If you are discharging from 100% to 60%, then your DOD is only 40%, right? Good. And the lower the depth of discharge is, DOD, the longer your battery will last. So you have here an example, 50% DOD, then you will have around 500 cycles. This is more or less 2 years. But if you discharge only with 30% DOD, which is discharging to a minimum SOC of 70, then you will have a longer lifetime here, up to 1,200 cycles, which are 4 years, 5 years, and so on. And this is also a design question, yeah? We know how much energy we need to have in the batteries to be able to run our system, but then it's our decision if we buy a bigger battery and use a smaller depth of discharge, a smaller DOD, or we have a small battery and we use a higher DOD. This is our decision. Depending on this, we have to replace the battery more or less often. I hope this is clear for you. If not, please let me know in the chat. Charge controller, what is the charge controller doing? It is making sure that the battery is not overcharged and making sure that the battery is not undercharged. So when the battery is charged, the PV connection is carried, yeah, not cut it, but it's open. so that no more solar energy can charge the battery. And at night, when the battery is discharged, then the charge controller disconnects the load from the battery so that the battery doesn't get into a deep discharge, which could damage the battery. So the charge controller is taking care of our components, taking care of our batteries. Now let's focus on the solar system design. We want to know how many PV panels we need. At the end of the day, we want to know how much watt peak we need to have, and we need to know how many batteries we want to have. In this case, we are willing to know how much watt amperes we want to have, right? We don't necessarily need to decide how many amperes hours we need to use, because this will depend a little bit what is our decision in terms of having a bigger or smaller battery with a bigger or smaller DOD. But we need to know how much energy our battery needs to store to make our system run. Okay, so we will working with energy, watt hour, sorry, and watt peak for the PV panels. Let's have a look to the equations. This is the irradiance. Sorry, I'm realizing I use it here, the word G for the solar irradiance, but this is wrong. G, it is used for the solar radiation. Solar radiation, it is in watts per square meter. And I, it is used for solar irradiation. And solar irradiation, it's watts hour per square meter and day. Okay, so this is what we need to know. G is the radiation, actual radiation, and I is the solar horizontal irradiance or irradiation, which is the overall energy in one day that we got from the sun. That's why you see here the equations with the I value. So the solar irradiation that we actually get from the PV panels is the average one from the weather conditions, but then we have losses, right? We have losses in our systems. We have losses because the PV panel is not always orientated in the best way. We have losses because the temperature of the cell of the PV panels are higher than the nominal ones. And then we have also other losses in our cables, in our charge controller, for example, and so on. And these losses, we can summarize more or less to simplify this on 30%. Yeah. So we can consider that 30% of the solar irradiance is being able to be converted by our PV panel into useful electricity. So at the end of the day, we have the to calculate the PV power, we have the electrical consumption divided by the corrected irradiance, yeah, which include already the losses. So let's have a look to this. Here we will have our load that we said is around 7.8, if I remember it well, kilowatt hour per day. This is electricity, right? Electricity. Good. Divided by the corrected solar irradiance. And now we have the question, how can we deal with this? Which solar irradiance should we take now for Nigeria? I told you we will be moving between 2 kilowatt hour per day and 6 kilowatt hour per day. But what should we do? Which value should we take? And we had it also from previous slides, which ambient temperature should we take, right? So now it is time to have a look to the weather conditions in Nigeria. So at some time, of course, during the process of the design of a solar cold room, you have to understand the weather conditions. So I invite you to go with me through an investigation on what are the weather conditions in Nigeria. And for this, we are going to use a tool from the European Commission. You have here the link. I would like also Anna, if she could put this link on the chat, or Oscar, so that everybody has access to this. This is a very nice tool where you can obtain typical weather conditions in any region of the world. We have here Nigeria and the neighbor countries. So you can see here, because of the color, you see here the tropical weather conditions you can more or less already see here. And above this, we have more subtropical weather conditions, and Nigeria is having tropical weather conditions in the coast, as you know better than me. And in the country inside is having subtropical weather conditions, and affected also by desertical weather conditions that are somehow extreme. Less rainy conditions, but higher fluctuations on the temperature. And we would like to understand it better. And you see here your country, Lagos, here Abuja, your capital, affected by warmer conditions. And now I would like to compare them with you, but you are free this afternoon or in the coming days to do the same exercise, compare different locations in Nigeria, and you will get surprised how different they can be. So a cold room working in Lagos will have a different design that a cold room working in northern cities of your country. So let's have a look comparing these two cities. Let's go deep in detail. First of all, we could calculate the average, or we could have a look to the average solar radiation in Abuja and Lagos. And you will see the average solar radiation in Abuja all over the year is, as you can see here in green, sorry, have a look here to the curve. So green is Abuja and red is Lagos. And so you can see all over the year, we have around 20% more solar radiation in Abuja. So we could think, okay, it might be a better location, but we don't know, because for solar cooling solutions, it is not only the solar radiation what is important, it's also the ambient temperature. If the ambient temperature is higher, we have less efficiency in our cooling units. We have also more thermal losses. So then ambient temperature is at least as important as solar radiation. Both are very important. We need to study both in detail to understand what is the type of weather conditions that we have. So let's have a closer detail. We have to assess the global radiation all over the year. So this is from January to December, all over the year. You see here the different days in Lagos in red and green for Abuja. And then you see something which is very interesting. You can see in Lagos, you have much more rainy days than in Abuja. I think everybody can confirm this. Lagos on the seaside affected by the more tropical weather conditions. You can see it for example here in June and May. The amount of rainy days in Lagos seem to be quite high. Let's have a zoom to this. Let's have a closer look to this. Okay, so you see in Abuja, okay, the solar radiation is normally higher. Almost every day is higher than in Lagos. But what is not helping for a cold room in Lagos is the solar fluctuation. So you see here, rainy day. This is a very rainy day here. Very low solar radiation, solar irradiance. In Lagos, then you have here another rainy day, here another one. Here you have also a very bad one, and here a very bad one. So to design a cold room in Lagos, we will need to consider that we have a sunny day and then a very rainy day. And then again, a sunny day, a rainy day. We might have 2 days, consecutive rainy days. So this is important for the design of the cold room. In Abuja, as far as I have seen, the rainy days, they don't go so deep on the solar irradiance than in Lagos. So this will be here the worst case for Abuja, which is actually having more or less double as much solar energy than in Lagos in a worst case scenario. So the design for the in terms of solar radiation, it is more comfortable in Abuja than in Lagos. I hope everybody agrees on this. These are typical weather conditions. But what about the temperature? Let's have a look to this. The temperatures profiles are very, very different. You see in Lagos, here in red, the daily average, not the average temperature, but the fluctuations during night and day, they are about 5 degrees here in January. Then in other months of the year is even lower. So Lagos, it seems it has a very stable ambient temperature during the day and during the night. Abuja has much higher fluctuations on the temperature. So we see here maximum temperature 36 degrees in February, this is average, and 23 at night. Of course, you have days with 40 degrees, right? No question about this. But this is the average fluctuations between day and night. And then I will say, if we are running our cooling units during solar radiation periods, then in Abuja, we will deal with lower efficiency in our cooling units than in Lagos, right? Because the ambient temperature during the day is always higher in Abuja than in Lagos. And this we need to consider in our design. So we need to understand very well the weather conditions at the location where we are installing our cold room. It will make a big difference. Of course, we are not going to do a research on this now because we have simulations, we have design toolboxes that we will use on our next webinar. But I just wanted to have a look to this. The critical weather profile at both locations for me seem to be in May. So the May is a critical month because the ambient temperatures are quite high in both locations and the rainy days are quite often. So what I did is I selected for Abuja this worst case scenario, this rainy day, and for Lagos I consider this as a worst case scenario, yeah, because we want to design our PV panels in a way that they are running during rainy season. If they are running during rainy season, then they will run all over the year. And if our cooling units are able to deal with warm days, hot days, then they will be able to run all over the year. So this is when you are doing a design by selecting one critical weather condition, then you need to do it like this. If you are having a simulation model that is calculating all over the year, then you of course calculate a typical year, and then you see what's going to happen all over the year. But now for our calculation today, I selected a critical weather profile for both locations, Lagos and Abuja. You can see here the ambient temperature of both locations, and what I summarize here is I had the worst rainy conditions and the worst hot conditions at both locations, yeah? And this is interesting. When it is raining, then we have here Abuja is blue, Lagos is gray. So this is Lagos global radiation, solar radiation, and this is Abuja. Abuja has always more solar radiation than Lagos. The temperature in Abuja is red, is higher than in Lagos, yeah, but it's moderate. It doesn't go over 30 degrees in any of the sites. When we have hot conditions, then the solar radiation is normally very good at both sides, as you can see here, yeah. But the ambient temperature is higher, going up to 37 degrees, especially in Abuja. Yeah, so this is the way we are trying to understand the weather conditions at both sides. Yeah, we have worst case rainy conditions with low radiation, moderate temperatures, and worst case hot conditions with high ambient temperatures but at the same time high global radiation. Okay, what can we do? Then we take the very worst case scenario. We take the high ambient temperatures and low radiation, yeah, which will typically never happen, but this is for us now the worst case scenario for our cold room. So our worst case scenario is we have this ambient temperature here in black, ambient temperature going to 37 degrees at night to 22 degrees, okay, and the global radiation will be like this, yeah, it's around 2.3 kilowatt hour per day. So already what I told you before, you don't find a worse day than this. So it is not necessary to consider zero solar radiation because you always have a certain solar radiation. In your case, in your country is 2.3. Okay. This is the worst case scenario. Another worst case scenario is that the products to cool down are cooled down overnight. Yeah, we are doing it like this because then our ice storage has to deliver the energy to the products during the night without cooling units, so to say. That's why you see here the weather conditions starting on the night and then we have the day. Okay. So those are the weather conditions we are using. Now let's continue with our equations, right? You remember we were missing on this value, but now we have investigate the weather conditions and we have a good feeling. We can use 2.3 kilowatt hour per day. And if you enter here the 7.8 kilowatt hour and here you enter the 2.3 minus 30% losses, if you remember, 30% losses, then the design will tell you you need 4.2 kilowatt peak PV panels. So 4.2 kilowatt peak or 4,200 watt peak. So if we have PV panels of 350 watt peak, then we will need around 12 panels to have this energy. Remember, this is the very, very worst case scenario, right? We will never need something like this, and we need always to do a fine-tuning design with a simulation model that is telling us, okay, you can actually design with a little bit less or much less PV, or you can design it on a way or another. This we will do in our next webinar, but now we are calculating the very worst case scenario. So for this, imagine every single day of the year is a very worst case scenario. Then you will need 12 PV panels with 4.2 watt peak. What about the battery? The capacity of the battery in amperes hours, it is calculated like this. You need to have the load, electrical load. And here, if you remember, we are using 7.8 kilowatt hour per day. Autonomy, actually, because we are working with the worst case scenario, we don't need any autonomy because we are already calculating that we are in the worst case. So autonomy can be 1 day. So it's just the energy we need for this critical day. Then we have the voltage of the batteries, 12 volts. The efficiency of the batteries, we can consider around 90%. And now we need to decide what is going to be our SOC minimum that we want to have. And what I selected here is 60%. So we don't want to have our batteries discharged below 60% SOC, because this is going to deliver us a good lifetime for our batteries. And I mean 60% in the worst case. Normally during sunny days, the SOC will be higher than this. And if you calculate this equation, you will come to 1,700 amperes hours, yeah, which are 21 kilowatt hour energy that we need to have in our batteries. So if we have batteries of 100 amps, then we will need 17 batteries, which you can see is already a lot, right? A lot of battery capacity we need. And that's why we need to use thermal storage. That's why we need our ice storage. What I did right now is a typical calculation of a solar system without thermal storage. So now let's have a look, how can we reduce the amount of electrical batteries if we are using ice storage? So this is our calculation without ice storage. We will need 1,700 amperes hour. And now let's have a look to our thermal storage, because what we can do is we don't need to store the whole energy in the batteries. We can actually deliver energy directly to the water chiller, to our ice storage, and then save the battery there in form of ice. We have the option is open, yeah, we can have bigger batteries, more or less cooling units. Now let's have a look how we deal with this. Here you find again the thermal energy we need for our cold room. This is the electricity we need if we consider that we are working with a COP of 1.75. Yeah, so this is electricity, this is thermal power. And based on our calculation, the PV panels need to deliver this energy. Now the question is, are we delivering it 100% directly as ice storage, or are we storing a little bit on the batteries and then delivering? Yeah. And as I told you at the beginning of this webinar, we are doing a mixture. We are not working totally battery free, because then you will need a lot of cooling units, because the amount of hours that you can run the system will be only around 6 to 7 hours. But we have small batteries that allow us to run the cooling units at night also for a couple of hours. Let's have a look to this, how we can deal with this. For this, I prepare an Excel file that we will use also in the next webinar. And what I calculated is the PV power based on the PV panels we calculated and the solar worst case radiation that I calculated. Yeah. So this is the power that we are getting along the day. So have a look here. We are going from hour 0 to hour 23, so 24 hours at the end of the day. The battery SOC is calculated here, and then we have here a factor if the cooling units are on or off. So the cooling units are on so long the battery SOC is above 60%. Yeah. So you see here we have 5 hours, 6 hours at night where the cooling units are working. Then we have a time where the cooling units are not working. Yeah. 9 hours. So 9 hours the cooling units are off. We don't want to run them. And then as soon as the sun is there, you see here the solar radiation is starting here. Then the cooling units are charging the batteries first, and then the cooling units are again running. So in total, we have 15 hours where the cooling units are running and 9 hours where the cooling units are not running. So this is now my suggestion for the design. There are, of course, different variations of this. But if we do it like this, that the cooling units are allowed to be stopped for 9 hours per day, 9 hours per day, yeah, at night. Then I did the calculation for the battery that we need, and I came to this value. We need 4.5 kilowatt hour batteries. We need a little bit more of PV, so not 4.2 but 5.5. So you see, we increase the PV, we reduce the battery a lot. We need 8 cooling units. We need 8 cooling units that are delivering the overall cooling demand in 15 hours per day. And we have a water chiller with 500-liter water. Yes. And then let's have a look here to the cooling energy generation is happening here during the time where the cooling units are running. And then we had here a calculation of the water chiller temperature. So we are starting at 2 degrees and we are ending at 2 degrees. But in between, the water is helping us to provide cooling energy during the time where the cooling units are not running. So let's have a look here to the water chiller temperature. We are starting here at 2 degrees. So this is the temperature indication, 2 degrees. Then during the time where the cooling units are working, they are going down. Then during the time where the cooling units are not working, the temperature is going high, up to 8 degrees. I'm considering we don't have ice, just to make it with water first. We will consider, because, you know, if we will have ice, we will be stable at 8 degrees, at 0 degrees, sorry, and then we cannot figure out it so well. That's why I'm using water. Then we go up to 8 degrees, and as soon the cooling units are running again during the day, then the temperature decreases again. So you see, the system is working. We are always having cold water to deliver power to our cold room, but the cooling units are not working the whole day. They are only working 15 hours per day. And depending on the configuration, we will have more or less cooling units, more or less batteries. This is providing us, at the end of the day, 2 different scenarios. So we can have a calculation, a design of a cold room without ice storage or with ice storage. Let's have a look here to the calculations. Without ice storage, we have 2.2 kilowatt peak for PV, and for the batteries, we need 21 kilowatt hour capacity. Yeah, these are the 1,700 amperes hour that we calculated. If we have ice storage, we can reduce the amount of batteries to 8.5 kilowatt hour, sorry, and we increase a little bit the PV. We could have, for example, another scenario. We will do it in the next webinar to have it totally without batteries, so that you can see how many cooling units we need, how much more PV we need. So you see, we'll have always different scenarios, and we can select. For me as a designer now for Nigeria, because I know the batteries are expensive and I have to replace them, this will be for me the best scenario because of this reason. The overall cost at the beginning is $8,000, 400. This, I consider that every watt peak is costing $1 US, and I'm considering every watt hour battery is costing $0.2 US. Yeah, this is an estimation. You can perhaps for the next webinar prepare also or help me to have real prices, but this is the prices we know from other from Nigeria and other countries. And based on that, we have for this case $8,400 US, and with ice storage we have $7,200. Yeah. After 5 years, where the batteries are over, we need to replace them, right? And this is what costs a lot of money, another $4,000. With the ice storage, we only need to replace $1,200. So after 10 years, we have saved with the ice storage around $6,000, which is 60% of the overall cost of the solar system. And that's why it is important to work with ice storage, with thermal storage. That's why we do this. And the question is always, do I use more batteries or less batteries? Because this will affect the amount of cooling units that I need. I advance you for the next webinar that without ice storage, we will probably be able to work with 4-6 cooling units, and with ice storage, we work with 6 to 8 cooling units. And without battery at all, we will probably need 10 to 12 cooling units. Yeah, so this is the amount of cooling units. And depends on how much we pay for the cooling units and how much we pay for the batteries, we will find in our next webinar our optimal, our cold room that is designed in a way that we have the best cost efficiency. And this is going to be done thanks to a cost optimization that is integrated in our design toolbox. The design toolbox includes all the calculations we have done today. It includes weather data, information about the product, economical information. So very important to know how much do I pay for a watt peak, how much do I pay for a battery in Nigeria, how much do I pay for the sandwich panels. So my question will be if you could prepare for the next webinar on the local cost of sandwich panels of different insulation thickness, on the PV panels, on the batteries, and the cooling units price. We will let you know on our next session, because this economical information is very important for the design. Yeah. And this is very interesting. Normally, a system is designed on a way independently on the cost of the components. But in our case of a solar power cold room, we need to know the prices of the components because we have several variations. We can insulate more or less. We can have more or less batteries. We can have more or less cooling units. And depending on this, what is the cost of the different components, we will get to the most cost-efficient design for our solar power cold room. The results will tell us the design, the final design for PV and batteries, the design of our ice storage, and it will help us also to let us know about the payback period that depends on the income generation of the solar cold room. This we will do in our next webinar. We will send you the Excel files in advance, and we will request also you to do a small research on the cost of the components in Nigeria, so that we are prepared to go not only in the engineering design, but also in the economical assessment of a solar power cold room. This will be on July 5th, if I remember well.
Yes.
Yes, July 5th, and we will provide more details when the dates are coming closer, and we'll have also a face-to-face training with this and much more information about cold rooms in September this year in Ilorin at NINSPRI. Thank you very much for your attention.
Okay, thank you so much, Dr. Zablatira and Dr. Torres. I want to thank you both for sustaining this. I want to believe for everyone it has been an engaging session. For those of you that are just joining this for the first time, I did mention last week during our panel session that the goal of having all of this is to be able to raise a team of experts who will not only be able to construct cold storage technologies in Nigeria, but I will serve as experts for maintenance, for operational purposes. So as we all do this, I will want you to try as much as possible join the next webinar, and most importantly, God willing, September 5 is the date for our physical training that will take place here at our headquarters in the lorry. So please feel free to continue to contact us if you have any question thereafter now. You can always send an email to the email for attending this webinar session. All my colleagues who has been on this committee with me, I appreciate all your effort as well. And we will meet again July 5 this year, God willing. Thank you, everyone.